president of the Iowa State University Physics and Astronomy Club. I don't know if any of you guys actually like physics. I know I see a bunch of students. So sometimes students don't like physics because of the math. So we're going to keep all the equations out today. We're just going to show you our favorite demonstrations and hopefully teach some of the basic physical principles that we learn through these demonstrations. I think the show is sort of partitioned up into 3 different sections. The first one is on sort of energy and forces and classical stuff that's been around since Isaac Newton for 400 years. It's really the basic stuff that a lot of people think of when they think of physics. Next we'll do a couple demonstrations on sort of temperature, hot things and cold things and why they're interesting. And then we'll finish off with electricity and magnetism, one of the most useful parts of physics that we think you guys will enjoy. So I guess first we will start off with a classic experiment, a classic problem that we usually work in lots of our introductory courses. And I think Kurt is going to take it away and tell us about the monkey gun experiment.
Alrighty, hi everybody, I'm Kurt. I'm the secretary of the ISU Physics and Astronomy Club. And we're doing, this is the monkey gun experiment. So the setup of the experiment is there's a monkey hanging from the tree, and we're going to use a target today because I used our last monkey on the last show. We're going to use the target, and I'm going to be the poacher. And so, how it goes is that the monkey is hanging from the tree, and the poacher is aiming his gun at him, and it's a very clever monkey. So just as I fire the gun, the monkey lets go of the branch. And so he falls as I shoot. So the question is, where should I aim to hit the monkey? Any ideas? Down below the target. So that's one thing that can happen.
Any other suggestions? This is an interactive show, so if you have any questions, feel free to just yell out if you have answers.
At the monkey? And why would I aim at the monkey or below it? So, yeah, as it leaves the gun, both things are false. Did you have something to say? In the middle?
All right.
Well, I'm going to take an executive decision and aim at it, and I have a laser pointer on here to let you know where I'm aiming. But yeah, as they both fall, or as it leaves the barrel, they should both be falling at the same rate. So we'll see if my marksmanship.
Yeah, this is the most pressure of any of the experiments. So, I don't know, are you pointing at the target? Hey, we nailed it. So what do we learn from this experiment? Anybody? Physics is fun. Yeah, sure. Physics is fun. Physics is dangerous. The two go together sometimes. Who knows? What's up? Perfect. The force of gravity pulls on everything the same. So the bullet, as it's traveling through the air, is going to drop at the same rate as the target. So they're going the same speed, so they're going to hit. That's why we aim at the target, and that's sort of a conceptual question that we always pose. And I guess that's our first sort of lesson for today. So, any other questions about the monkey gun experiment?
Where's it aim when the monkey's face off the tree?
Above it, right? Because your bullet's going to fall? Oh, you can calculate that, but we're not doing that right now. So thanks, Kurt. And I think next we're going to start talking about a few conservation laws. I know, big word, right? So a conservation law is a really, really powerful thing in physics. What it says is that there's a quantity in a system. We've got, say, in the bowling ball that Mike's holding, that we have a system, and there are quantities that stay the same no matter what you do. So one of these is energy, and Michael is going to tell us a little bit about conservation of energy in the bowling ball kits.
Hi everyone, my name is Michael Fellerman. I'm a junior here at Iowa State, and major is physics, obviously. But what I'm going to show you today is a little demo called the bowling ball kiss, and we call it that because you get to familiarize yourself quite well with the bowling ball.
He really likes bowling.
You become really friendly with the bowling ball. But what Andy was talking about is this idea of conservation of energy. All that means by conserve is that if you don't add anything to the bowling ball or this system, if you don't add anything or take anything away, it can't gain or lose energy. So if I was to stand against a wall like this and put the bowling ball up to my face and let it go, what do you think is going to happen? Will it come back? What's going to happen? It'll swing? Will it hit me? No. Alright, let's see.
We'll hope. Unless we rigged it up because we don't like Michael. Then we'll see, right?
Yeah. You wanted it to hit me, didn't you? No. So all that happens is that when I'm against the wall and I have the bowling ball up, I let it go, and it picks up speed because gravity is pulling it down. When it gets to the other side, when it gets to as high as it can go, it loses all of its, what we call kinetic energy. It's energy due to how it's moving, because then it doesn't move anymore. But it's picked up a lot of what we call potential energy. It has the potential to fall back down. So then it falls back down, comes towards me, but by the time it's reached my head again, it's lost all of its motion, it's lost all its kinetic energy. So it can't come any further and it won't hit me in the face, luckily. Thanks, everyone.
So that's our first and one of our most important conservation laws. It's called the conservation of energy. The energy might change form. It might be due to this potential of Michael having to lift the ball up and then drop it. It might be due to the ball moving. But however the energy is present, it's always there and it's always the same amount. So next we're going to talk about a different conservation law. It's going to be called conservation of momentum. And that has to do with how fast things are moving and how big they are. And I think Preston is going to tell us a little bit about conservation of momentum using Newton's cradle.
Hi everybody, like I said, I'm Preston. Everybody's seen one of these before, and it's a wonderful experiment to explain conservation of energy and momentum. I'll bring it up, it kicks another one out. Because this has so much momentum and so much energy, it transfers right through this set of balls and right to the other one. Newton had 3 laws. There was one that said an object that is in motion tends to stay in motion unless another one acts on it, such as this one, and it stops it. And the third law, most relevant to this experiment, is that when 2 objects collide, this one has some force, and this one opposes it. It has force that will directly oppose it. And you can see that this transfers all the way through to this one. So, a little thought experiment here. We're going to try a couple different cases. We'll do 2 balls, and as you probably expected, 2 of them kick off. Now, let's try 4. And the momentum carries through in the exact same way. And now the most interesting of all, this one's a little more difficult to time out, but it's a wonderful experiment to explain Newton's laws.
So that's Newton's cradle, right? So that's our second conservation law, the conservation of momentum. And next I think we're going to go to a sort of a new demo that I've only seen a couple of times now. I think Paul is going to tell us about whatever's in his magic rolling can.
What's up, everybody? I'm Paul Estes, and I'm a sophomore in physics. So what I have here for you is a magical can. As Andy has said, I don't think of it as much of a magical can as it's just my can that I can bring in and show off to everybody. So if you guys have ever played pool, anybody ever played pool or shuffleboard? I'm sure most of you have seen that. Yes. So when you're playing pool and you shoot a billiard ball, Eventually it comes to a stop, even though it seems like the pool table is so smooth and the pool ball is so smooth. Eventually it'll come to a stop due to friction and heat loss. So what I'm going to go ahead and show you here is just basically that, is the can coming to a stop here. But one thing about physics majors that you guys might not know is that we actually have the ability to warp the laws of physics. So if I can maybe get the try.
He's our resident Jedi as well.
Alright, that's as far as I can get it. So, does anybody have any theories as to what's going on with my special can here? It's a hamster.
That's actually what I've never heard.
So, hamster safe. Any other theories? Nothing? Alright, well, I'll go ahead and explain it for you, because I see a lot of dumbfounded looks. What's on the inside is actually a rubber band with a weight suspended in the middle. And as we've heard from conservation of energy, conservation of momentum is, I can't just throw the can and magically it's going to come back. So, unfortunately there's no hamster in there, cute and cuddly to pet afterwards, I'm sorry. But what happens is that weight is going to stay suspended in the bottom of the can essentially, and the can's going to roll up and twist up that rubber band. Then as soon as it stops at the end, that rubber band still has all that energy twisted up in it, and so now the weight's going to pull down on it and twist it back and bring it back. So, any questions on that? No answers, I'm sorry.
So that's the magic rolling can. Thanks. And you know, the other thing that the rolling can sort of demonstrates is really the process of how physics actually works. We'll see something in nature that's really sort of odd or not intuitive, something we want to understand. The can rolls and it comes back. We don't expect it to come back. So we wonder, well, what's making it come back? So you guys were putting out theories, a hamster, of why it comes back, and then we test them. In this case, it's easy enough that we just open the can and look inside and we can sort of figure out how the can works. But
And in this thing are going to be our system, while we're actually going to add some things to it. It will depend on how fast it is spinning, which is called angular velocity spinning, and the mass and a distance. And this is, of course, going to be our distance, and these weights.
yeah, we'll go for safety, right?
We don't want broken necks. All right. So now we have this mass at a certain distance from the center of rotation. And I'm sure if you've watched the Olympics, you've seen this, what we're about to demonstrate. Figure skaters like to explain this. They'll start with their arms out like this, and they'll be spinning at a certain speed, and they'll pull them in, and they'll actually spin faster. If you don't believe me, we'll do this now. So Denise is going to start out with her arms out. I'm going to give her some spin, or angular velocity. And she's going to pull her arms in, and she spins up quite a bit. And gets dizzy. And she pulls back in, she spins a bit more. Yeah. I'm going to give you more this time.
That's
Actually, if I were to do this, since I have longer arms, it would be more dramatic, since I would have the mass at a larger distance from the point that she's rotating about.
and I'm sure at this point she'd like it.
She claims she doesn't get sick, but
I didn't today,
but
so.
Just in preparation for you guys. Yeah.
all right. And now we have what looks like your standard bicycle, and we're going to give it some spin. It's going to spin in a certain direction. Now I'm going to hand this to Denise. And as you can see right now, she is not rotating. But if she rotates that around 180 degrees, she rotates quite a bit. And you can't see it from up there, but she is actually rotating in a direction opposite to the rotation of the wheel. By twisting that, she is actually changing the angular momentum of the wheel, but has to remain constant in the system. So then she has to rotate to compensate for it.
Kind of an issue.
You know, this must have really freaked some guy out at some point.
So this is also the same thing that actually keeps you upright on your bicycle when you're moving. When you're standing still and you're on your bike, you know, you just sort of wobble side to side. But when your wheels are going forward really fast, the wheel doesn't want to go one way or the other, so it's a lot easier to stay upright. So thank goodness for conservation of angular momentum, or else we would not be able to ride bikes, right? All right, so any questions on the angular momentum machine? Okay, so thank you, Denise and Sally. So those are our 3 conservation laws that we're going to show you today. We've got conservation of energy, the conservation of linear momentum, and the conservation of angular momentum, or the conservation of spin. So next we're going to sort of change topics a little bit. We're going to talk about thermal physics, sort of. We really are just doing these experiments to blow things up, which is coming up. So anybody know what makes hot things hot on a molecular level? I know, yeah, some of you are in college, so you should. So hot objects have molecules that are moving really, really fast. They're going fast together. They're going a lot faster than cold things. So that's sort of what we say is when things are hot, their molecules are moving fast. When things are cold, they're very, very, very slow. So next we're going to make some hot gases. This is what I'm going to do for the experiments today. Because I'm a senior and I want to go out with a bang. I've got balloons filled with hydrogen, oxygen, and a combination of the two. Does anybody have any ideas of what's going to happen when I light them on fire? An explosion maybe, right? Good, we all like explosions, lots of danger. So first I'm going to light the hydrogen balloon, just hydrogen by itself. This may be kind of loud for those who have small children or, I don't know, really don't like loud noises. You might want to cover your ears or step out, step out in the hallway to the next. Oh, okay. Sounds good. So I'm gonna light the hydrogen balloon now, okay? On 3. 1, 2, 3. Maybe. There we go. So that's a pretty good flame, right? That's all right. So what's gonna happen when I light just the oxygen balloon? Ideas? It's gonna blow up too? Yeah. It'll just make it brighter. So we think it's going to make it brighter. What else do we think? I heard something over here. Yeah. Louder? Anybody else?
Slower.
Slower. All right, well, now we have lots of theories. Let's do the experiment. So here is just oxygen on 3. 1, 2, 3. So it didn't do anything, right? So we know that hydrogen burns, but oxygen does not. Oxygen actually aids in combustion. It aids in the explosion. But it isn't actually what is sort of exploding, if you will. So, what do you think about the hydrogen-oxygen combination? I kind of just gave it away, but what do you think? This one you might want to plug your ears. Yeah, this is a big boom. If you don't know, hydrogen and oxygen, it's great because of water. It's also great because of rocket fuel. This is what they use in rocket fuel. They combine hydrogen and oxygen. So here's the Big Bang on 3. Ready? 1, 2, 3. That's the important part. This is a lot of fun, right? So anyway, from really hot stuff, we're going to move on, and we're going to talk about liquid nitrogen, which is really, really cold. So I think we'll just let Denise take it away from here. You're all set up, right?
Yeah.
So here's Denise with liquid nitrogen.
So he just showed you a really awesome demo, and I'm about to show you an even cooler one. And here I have a dewar of liquid nitrogen, and a dewar is just a fancy pretty much, that has a vacuum on the inside of the two walls to keep it from getting heat inside. So we have some liquid nitrogen in there, and you can see that it's kind of steaming, and that's because liquid nitrogen boils at negative 321 degrees Fahrenheit, which is 533 degrees Fahrenheit less than the boiling temperature of water. So it's really, really cold, and we have some balloons here. What do you think is going to happen when I put a balloon with just regular air into the liquid nitrogen and cool it down? It's going to shrink. And why is it going to shrink? What's happening to the molecules inside the balloon? They're slowing down, yeah, because they're getting colder. So the air in the balloon actually doesn't go anywhere. It's just going to turn into a liquid, and it's going to shrink. Does anyone know where we get our liquid nitrogen from? Well, not like, from another big river or something, but like you can't just find it on the ground, right? So it comes from the air. The air is 80% nitrogen, so we just pull it out of the air, cool the air down, and take out the nitrogen. All right, so now it's nice and shrunk. And it's warming up now, so it's getting bigger. The molecules are becoming faster, and it's going to get back to its regular size, the size that it was before I put it in. And here I have a squeaky toy. And squeaky toy is a solid, so it's going to get cold, right? But what's going to happen whenever I put it in there and it gets really cold? Yeah, it becomes brittle. That means it's just getting more solid, right? So it's not going to have a state change, but it is going to get cold. And it takes a while for this one to get to equilibrium. So while I'm doing this, does anyone know, like, maybe who uses liquid nitrogen? What are some uses for it? Cooling systems? Yeah, it is a cooling system for maybe food. McDonald's is the #1 consumer of liquid nitrogen in the United States. They use it to cool down their hamburger patties. And we also use it to cool down magnets in like the LHC and the Fermilab, the accelerator, particle accelerator rings, and to cool down telescope mirrors. So it's really important for physicists. Okay, now it stopped boiling as much, so I know that it's come to equilibrium. And I'm going to pull it out. We're going to see what happens when I throw it on the ground. It shatters. So it was very brittle. And I can put my hand in liquid nitrogen for just a little while. You don't want to hold your hand in there. But I can just pull it out, and it's fine because the liquid nitrogen is boiling around my hand, creating a film that protects it. So.
We had a guy from the Environmental Health and Safety Department that was here last time and wanted us to tell you that it's very important to wear goggles when you're using liquid nitrogen. So we're sorry we're not following correct safety protocol.
Don't put it in your eyes.
But we promise we won't splash grease in our eyes.
Yeah, as long as I don't like roses.
Yeah, sure.
Are there any questions about liquid nitrogen? Thank you.
So those are sort of our two fun thermal physics experiments, if you want to call them that. It also sort of demonstrates that a lot of physics happens at extremes. That's what a lot of times what physicists study. It's not just normal everyday things we run across, though that is something that, very smart people have done and are currently doing. But a lot of times we study weird things like, how things explode or things at very, very, very cold temperatures. So next we're going to move into our third section of the show. It's on electricity and magnetism. We're going to start out with an experiment that you've probably seen before. It's done in a lot of high schools. Your parents have probably seen this in their high schools. It's been around for a long time. It's called a Van de Graaff generator. And Matt Lampy, I think, is going to tell us more about static electricity and the Van de Graaff generator.
Hi everybody, like Andy said, my name is Matt Lampy and I'm a senior here at Iowa State in physics. This is a Van de Graaff generator. You might have seen them at like museums or something like that. In general, what they tell people to do is put their hands on it and their hair stands on it. They have a lot of those. Basically how it works is we have a belt that runs around up through this metal ball and it deposits static electricity up in this ball. It'd be a lot like if you rubbed your feet on a carpet and then touched your car or refrigerator, you get that static shock. Same thing, except just a lot more static electricity in this ball. This one's a little more powerful than most you'd see in a museum. We don't really like to put our hands on it, so we made hair for it instead. So we'll just put that on top here.
Also, I would normally do this. My hair is about 12 inches shorter than it was last week.
We were disappointed.
So we'll turn this on. Alright, so if you were to have your hand on this now, your hair would be standing on end much like this string. What's interesting about this is all of the static electricity is actually running up through the ball and then up through this aluminum cylinder and concentrating out at the ends of each piece of string. And that's why they all stand up like that, because all the electric energy is concentrated out at the end. So if we touch one of them with the ground, they fall down. And if we ground the entire ball, they'll all fall down. So. Like we said, there's quite a bit of static electricity that's made by this machine. Another cool demo that we like to do with this is we take these pie tins, just normal everyday pie tins, and set them on top of here. Now, what do you guys think will happen to this?
It's our version of flying saucers, I think, right?
The reason that happens is because the pie tins get electrified one at a time. The top one gets electrified and it flies off because it repels the ones below it, and then the bottom one, and then so on and so forth, the other pie tins. So that's our Van de Graaff generator.
So next up, Tyler's going to tell us about a Tesla coil. It was invented by Nikola Tesla quite a while ago, over 100 years. And this is actually a Tesla coil that Tyler built himself. He's sort of an enthusiast, if you will. He's built a few of these Tesla coils, and he agreed to bring this one up and show it for you guys today. I think this is a really cool experiment. I'm a fan. Not to build this too much up for you, Tyler, but it better work. Right? So.
Tyler. I am a junior in physics here at Iowa State. So, I built this S coil during high school for a science fair, and it's managed to live throughout the years, so it still functions pretty well. So, it's an electrical machine that basically is used just to generate lightning. When it was originally invented, it was used more for wireless energy, but really, it's a lot harder to build one just for that, and it's a lot easier just to make lightning. So, and it's more expensive.
Yeah, and it's more fun, right?
Yeah, so basically how it works, in pretty simple terms, you just plug it right in, through here. I can control with this little machine here. When it runs in, this little part over here charges up and stores energy. And when it's stored up enough energy, in this PVC pipe are two copper pipes kind of lined up just like this. These are called capacitors. When they're charged up enough and have enough energy, they can actually arc across, and electricity goes right through the air, across these pipes. When that happens, all the electricity runs through this coil up here. And this is where we talk about something pretty common in electricity called a field. It generates an electric field, and that runs in the air, basically everywhere, but mostly directly up, and it goes through this coil. And this also deals with a phenomenon, I guess, common in physics called resonance, where it goes up and then down, kind of like a wave you'll see. And if you make this Tesla coil correctly, it'll arc across these copper pipes just in time when this comes down to push it back up. And if you get this going up and down in the right frequency, this will build up enough charge to make lightning. So let's see if, one disclaimer. Does anyone have a pacemaker? All right. Yeah, if you have a pacemaker, it's just, go to the back. But we should be good to go. Okay, let's give it a shot. The fan is used to cool off the copper pipes so they don't overheat. Oh, it's going to be loud. Not too loud. Demonstration of how the electric field works and how powerful it is. So I put this thing on top. Basically, it's kind of like the opposite of an antenna. Instead of gathering in, it's more efficient at throwing the lightning in. I have to tune the coil to make sure that it's still resonant, because adding this thing to the top changes the frequency that it rises and falls. So changing the coil will make it match again. So putting that up also gives me more lightning. And now what I'm going to do is I'm going to show that the electric field is powerful enough to actually charge this tube. The electric field will run through the tube, through me, into the ground, but it'll light this up. So let's see, make sure this works. Okay.
I think next up we're going to talk about, we're going to have, see, we're sort of changing things. The nails? Alright, so we're going to talk about electromagnets next. The important thing you need to know here is that when you have currents that run in a circle, they actually create a magnetic field. So like the electric field that was created by the Tesla coil, we are going to do the beat frequency thing. Okay, well first, before we talk about electromagnets, Sam's going to talk to us a little bit about beats.
First I'm going to show you the frequency, what do we call this?
Resonance.
There we go, resonance absorption.
He's a freshman, he'll learn, don't worry about it.
Sorry. Resonance absorption. I've got two bars here, they'll make frequency, and at the moment they're both going to make the same frequency. So if I start one going, its frequency that it sends out sound waves is going to hit this one and make this one sound out. Watch that. Turn that off, and that one's still playing. So that's pretty cool. Weird.
Okay, right there.
This one. Stick this on here. This is going to change the frequency of this one. So these two are now going to play different notes. And when this happens, the sound waves go out, and they're going to interfere with each other. Sometimes it's going to be constructive, sometimes it's going to be destructive. But what that's going to mean is that when we play these two notes together, you'll hear both notes getting louder and quieter, and louder and quieter. Let me do that for you. Sorry to hear that? Let's try that again.
Get them fast together.
There.
So you hear that waviness in the noise? That's because what he was saying is sometimes the sound waves add up and sometimes they subtract. So sometimes they cancel each other out. Right?
Okay.
Yes. So that's the beat frequency. So now we're going to talk about electromagnets. Magnets are really useful. We have them everywhere, every day. And I think, Mike, you're going to tell us a little bit about electromagnets, right?
Oh, I'll try. So what we're going to do here is kind of, have any of you seen seen in movies probably, like in the junkyards, they have those junkyard magnets, and they lift the cars up. Maybe, okay. So we're just going to demonstrate kind of a small scale version of that. What Andy was talking about before is when we have electrons or electric field going in circles, we'll make a magnetic field. Now, this rod here is made out of iron. Now, there's lots of different types of iron, but this is what we call soft iron. Now, it's not particularly magnetic. You see I've got nails here. They're also made out of iron. But this rod can't pick up even one magnet. But if we take this electrical wire and wrap it around a cylinder multiple times and run an electric current through it, it'll make its own magnetic field. Because like we said, electric field going in a circle will make a magnetic field. Now, if I put this iron rod inside the cylinder, where that magnetic field will be, it's going to change all the little atoms inside the iron, and it's going to line them up. And when that happens, then the iron rod will get a magnetic field, and it'll actually be a really strong magnetic field. So if I turn this on here, I'll close the switch, and I take this box of nails, what do you think is going to happen when I bring them towards it? Can we go to the nail? So you can see now, even though before it couldn't even barely hold up, well, it couldn't hold up one nail, now it can hold up quite a few. So this is just kind of a small scale, same thing, you know, cars have iron in them, nails have iron in them. So when you have the electric current flowing and have a pretty high magnetic field, it can hold up all these different nails. Because the nails want to fall, you know, you throw anything out that wants to fall, but the magnetic field is just so strong that it can hold up the nails against gravity. So what does everyone think will happen when I open the switch? It'll fall down? Because the current's no longer flowing. So since you don't have that electric field going anymore, you don't have a magnetic field, and you won't hold up the nails. So that's an electromagnet. Thanks, everyone.
Did you have a question? Say that again. Holding up
Yeah.
one?
Yeah, I was holding up one. It's still the iron rod. When I shut off the current, those little atoms that I said had lined up, they're still kind of lined up a little bit. What we call a residual magnetic field. But you know, once the bars, it's warm enough in the room that once you do anything to it, if it's warm enough, it'll, you know, disorganize them, or even, I think you can just hit it. I mean, they'll all randomize each other, and it can no longer hold up any. Any other questions?
All right, thanks, Mike.
Thank you.
So next I think we're going to talk about a kind of crazy concept called induction. We saw in this that a current going in a loop will actually create a magnetic field, and we know from physics that actually if you have a magnetic field that changes near something that can hold a current, that it will actually induce a current. And that's actually called induction. And I think Josh is going to tell us about induction when he gets out here. Maybe. Yay. This is kind of a cool one too. So it's always important to remember that when you think about induction, that you need to be able to sort of complete a circuit for this current. That it has to be able to go all the way in a circle in order to have a current set up. The induction.
Yeah. What I have here is called the induction loop. What we have is a solenoid, just a electromagnet pretty much, with an iron core here. And did you guys talk about induction?
I was just talking about induction. Do you want to say it again? Do you guys understand induction totally? No, not at all. You care a little bit, but so go ahead. Maybe you can go ahead and be.
What this demo is pretty much just all about is pretty much what happens when you have two magnets together. And if you have the north pole of two magnets together, I mean, anybody who's played with a magnet knows that they repel each other, right? Maybe you guys played with magnets, you know that they repel each other.
We do. We're physicists. Maybe everybody else is different, I guess.
this does is, when I press this button, when it's just plugged in, I have the switch on the opposite, so I'm not gonna do it now. But when I hit the switch, it'll actually start a current going around the outside of this ring. And when the current's going in through there, it will actually momentarily act like a magnet. And that magnet will actually have a reverse pole, so it'll be north-north. So this will be a magnet, this will be a magnet, and the north poles will be next to each other. So it'll repel. And we'll see that. So I'll put this on there. I'll turn this switch on. So, I mean, as you can see, I mean, for that moment, it's actually really powerful. I mean, it can actually lift it up. And kind of to prove that it's actually current going around there, around the outside, what we have here is it's made out of the same stuff. It's just, it has a break right there. I don't know if you can see it, but we don't have the camera, so we'll try it this way, and nothing happens. I mean, you can hear it. It's trying to, but it just can't establish the current going around the outside. And have you guys ever seen a demo where you have a current and then you make it really, really cold and you see that the current actually increases inside? Well, you can see that here. We have a ring that's actually in liquid nitrogen right now, and the current will actually increase when we have it cold, so the force actually increases too. So we might be able to get it going all the way to the ceiling.
Which I'm sure they would appreciate if we put a hole through their ceiling. But,
We won't. Nate, do you want to? Let's get that. All right, here we go. This is the temperature of liquid nitrogen. It's really, really cold.
more things you can use liquid nitrogen for. We have a professor that always tries to catch it on the tongs. He's really good at it. Josh is still trying. You try it one more time?
All right, try it.
That's kind of a cool one, right? So that is the induction loop experiment. So now we've learned about magnetism a little bit. We've learned about static electricity with the Van de Graaff generator. We've learned about Tesla coils. Now we know a lot. So we're going to look at sort of an interesting application. And first we're going to have Sam. He's going to show us something, an interesting little demonstration on what's called eddy currents.
So, what I've got here, a couple of little things here. One is a magnet, one is not. I'm going to drop them down through this tube. This one's not a magnet, this is just going to go straight on through. And that's just to show you that there's nothing in here. But if I take this magnet and I drop this down, what's going to happen is similar to the solenoid that you saw earlier, when Michael was turning the bar of iron into a magnet. He had an electric current going in the solenoid, which caused the iron to become a strong magnet. What's going to happen here is pretty much the opposite. I've got a magnet here, I'm going to drop it down in here, and it's going to make a current run through this bar. When that happens, it's going to act like a magnet in the reverse direction that this magnet is going. So when I drop this down, it's going to try and keep this magnet up instead of letting it fall down. So when I drop this through, it's going to go very slowly. Now I've got another bar here, and this one's got a slit through it, so that can't form a current. So what should happen when I drop the magnet down this? It's going to go fast again? Well, I'll admit that I kind of lied to you. There is a slight epoxy in here, so it is slightly connected. So it's not going to go quite as fast as the plain piece of metal did, but it is going to go faster than the sealed tube.
What do you think? That's the idea. All right, a little fast. So that's eddy current 6. So now in an application of sort of, at least a different demonstration of that sort of concept is Preston going to talk about magnetic rapes.
Hi everybody. When I throw this switch, I'm going to complete the circuit, and what's going to happen is you form a very powerful magnetic field between here and here. And a little bit of how it works is electric charges induce magnetic fields around them, and magnetic fields induce electric charges to go around them. We're using this concept today. So, if I can get a good swing, this thing swings along here, through the current, or the switch, and it stops immediately. Here's what's happened. The magnetic field induces those charges to start going around in circles. So you have little eddy currents, just as he demonstrated going through here, which cause forces to go out and down, and this stops it immediately. Okay. So, one other quick demonstration. I have another ring, or disc, with a bunch of slits in it. Tangled up. So let's hang it. And we don't expect this one to have any effect because those eddy currents can't form. If they did, I mean, the charge would just accumulate and charge doesn't tend to accumulate. But can't happen this time. Well, how can we apply this to something? It's kind of useless if it's just a silly trick. Well, we do have applications to that, like a magnet, those maglev trains. That's what they, that's what they work off of anyways. You can stop these trains very quickly. I'm sorry.
Roller coaster.
Roller coaster is what I was trying to think of. The train that you take at the amusement park, sorry. You stop those very quickly by inducing this principle. If you put regular drum brakes on one of those, you'd wear them out very quickly and they'd have to be replaced all the time, and that'd be very costly. So instead, they use this principle. You can stop them really fast and you get a nice thrill.
That's also the brakes that are used on the space shuttle. You can imagine your space shuttle is re-entering, it's coming in, it's really, really, really fast. Again, it's the same sort of thing. If you use normal brakes, you're just going to burn them up really, really fast. It's really going to create a lot of heat from the friction, and it's really not something you want to be in trying to slow down from those speeds. So they can use those magnetic brakes to stop the space shuttle without the heat accumulation, and it's maybe a little more expensive. That's why they don't really use them as normal brakes. But it is an interesting application of eddy currents. So next we're going to move on to sort of light and lasers. This is the 50th anniversary of the laser. It is one of a physicist's favorite tools. You do a lot of experiments. You got really high intensity lasers. Now you've got little laser pointers, personal lasers. I think Paul actually has his own with him today. And we're going to show you, I think, a little more about total internal reflection and fiber optics as well.
All right, so first I'm going to start off with a question. How many crocodile hunters do we have here in the crowd? Okay, we got 3, it looks like. So then I'm going to go ahead and draw you guys a picture and give you guys a little quiz. Let's see here. So let's say now, granted I'm not the best artist. Yeah, we're going to, yeah.
That's why you picked him.
All right. So let's say you're out crocodile hunting out there in, I don't know, say Florida or something, and you want to jump in after this crocodile. Let's see. So your direct line of sight is straight down to the crocodile. That's the actual straight line to the crocodile. So who thinks that if you're going to dive in after this crocodile, well, good luck first of all, but if you're going to dive after this crocodile, where do you want to jump? Do you want to shoot straight at that? Just dive straight at him and go right after him? Yeah, right down this line. Who thinks you'd look right at him, or shoot right at him? You're going to dive in after. Okay. What about dive down here so you can kind of, swoop in, I guess. Okay. What about above him? Come over top, maybe. Yeah. All right. Turns out the speed of light actually is slower in water. So it's because it's more dense. So what it actually looks like is because the water, or the light bends in the water, essentially, your line of sight is going to be something like this. So you're going to see the crocodile a little bit above where it actually is. So what you want to do is actually dive a little bit further away and not come down in front of them, because that would be bad. So what I'm going to go ahead and demonstrate here, if we can get this set up. All right, cool.
Well, you're in the way.
All right, and physics majors like lasers, so I have my own little green laser because they're entertaining. They're good if you're going out for, at a party sometime and you want to like entertain your friends, just bring a laser and light a lamp. You're that heavy. Yeah. All right, go on. All right, so I'll turn this light on. All right. Where's my screw? Oh my God. I am okay.
It's fun to work in the dark, right?
All right. All right, there it is. All right. I have this fun spray stuff. Makes physics more fun with a pH. Okay. Let's see. All right, so what I have here is, if you guys can see, the laser coming down into the water at this little angle here, and then it bends down into the water. And if you can see these, there are two lines coming out. And if you look up on the ceiling wall, whatever that is up there, there are two dots. All right. And this is because you have the reflection off of a mirror down at the bottom, and also the reflection off of the water. If I change, let's see if I can keep this going. If I change the angle of the mirror to such a degree, you see that that second dot actually disappears. So you only have that one reflecting off the top. And you have some going in as well. And you can see the light actually bounces off the top of the water on the inside. This is called total internal reflection. Got that wrong last time. So I guess now what I'm going to demonstrate. Okay.
Hit the lights for a second.
Yes, lights.
1 second.
All right.
Just in case, I don't know. We are borrowing the room.
Sorry, I'm trying to
So he's gonna aim.
All right. Let's see if I can get this in. And oh, sorry. All right. So this principle is something that we use a lot in optical cables, like telecommunications. If you've ever heard of stuff like that, it's the same principle we use for transferring information. And so another thing that I like to show is this acrylic tube here. It's the circle is in such an angle that the light going into it will actually just keep reflecting inside of itself. So if I take my fun little green laser, shoot it on the inside, circles all the way through. And that's the same principle that we use for sending information like through the internet or through your phone, not cell phones. So it's good.
So that's our total internal reflection experiment, right? Or do you guys want to shine it?
Oh, sure. Let's do more.
All right, we'll shine the laser a little bit more.
All right.
That's good.
All right. And
reflection. That's our second to last demo for today. We've got one more. It is a brand new demo, and it is actually really, really cool. It was built by one of our professors, actually, and it just got working a little bit a couple weeks ago, I think, something like that. So, before we do that, I'd like to see if you guys learned anything today. At the start of the show, we talked about 3 things that were concerned. What were they? What was one of them? Energy. I heard energy. Another one. Linear momentum. I'm going to ask my girlfriend what the third was. Angular momentum. Good. She knows. Okay. That's crucial. All right. So next we learned about a really important concept in physics that was demonstrated by the Tesla coil. Any idea what was that? Field. Yeah, it's a field. Okay. And then it looks like we're going to start the vacuum. Right? So yeah, what this does, this is called the vacuum cannon. We have a ping pong ball in this tube, taped off right here. We're going to actually suck all of the air out of the tube and then pop the tape and see what happens. So we've got a pop can down here you'll see on the other end, and we're going to tell Bert, who's in there, he's going to get out of the way so we don't hit him. Because theoretically, I guess I was told that this is supposed to be able to get up to Mach 1, so the speed of sound. So it should get moving pretty fast. So anyway, I guess while the vacuum's still being pumped, do you have any other questions about what you've seen in the show? Anything about physics in general? Maybe? Well, thank you all for coming then. We'll actually, after we do this, we'll have a couple of demos up here. Some of you might have seen the non-Newtonian fluid that we were playing with on the subwoofer before the show. We'll have more of that. We'll have, I think, maybe another couple of things.
We'll also have liquid nitrogen frozen marshmallows.
They're delicious.
They are delicious. Nitrogen is good for ice cream and marshmallows too.
Almost ready.
Almost ready? All right. Everybody having a good Veishea? Go Veishea.
Yeah. I want it to be a good one.
Keep going. Keep going. So like it so much. All right. I want to pop it.
That would be good.
Close your ears.
Yeah, this is another one that's going to be pretty loud. So, okay, so here we go. 1, 2, 3.